It is a pleasure to have Will Sawin from Princeton, and he's going to tell us about the fundamental groups of random three manifolds and other random objects.
Thank you. Yeah, I also want to apologize for the delay. I chose a flight time that I thought would allow me to help my lovely wife and my two lovely kids in the morning, and then make it here just in time for my talk. And then because of a little flight delay and some traffic, I made it here not quite in time for my talk. That's the reason for the delay. I will try to make it worth the wait. And I want to begin with so the first part of the talk, I'll be talking all about three manifolds. And so my three manifolds will always be oriented. They have some fixed orientation, and closed, meaning that they are compact and they have no boundary. And then probably the most important invariant of a three manifold, certainly a very important invariant, is the fundamental group, which is a colloquium at the very beginning of my talk. Let me briefly say what this is. So this is the group of loops to homotopy, the deformation of loops, and it's under the group laws given by concatenation. Loop starting and ending at a fixed point, and then you have another loop, and you combine them into one big. So let me start with a classical question in three manifold topology, which is which finite groups can be the fundamental group of the three. And so the answer of this is actually to do Perelman, because it follows from his proof of the geometrization conjecture, and the answer is the finite subgroups of SO4 that act without fixed points. Probably write a little bigger on S3. So SO4 is a 4x4 matrices, and they act on R4, and they preserve the metric, so they preserve S3, and they act on S3, and I'm looking for ones where no non-trivial element fixes any point of S3. And the positive part of this, constructing the three manifold, is easy. You take S3 and you mod out by your group G, and that has kind of G. And the much harder part of the theorem is to show that any other group cannot appear. For most groups, it's not that hard to rule out, and almost so the finite subgroups of SO4 that act without fixed points are classified. It's not much more complicated than the classification of finite subgroups of SO3, which is well known. And so there's a specific explicit list, and then almost all groups that are not on this list, it's very easy to rule out. And then there's a few that people were able to rule out by purely topological means before Perelman, and there were then Perelman ruled out the final groups by showing geometrization, which in addition proves that any actual three manifold with finite fundamental group must actually be one of these homomorphism. So now let me ask a slightly different question. What finite groups can be approximated arbitrarily well by phi1 of x? So that question I need to get precise. I need to define what I mean by approximated. So what I mean is that for all natural numbers n, there exists m such that g is a quotient of pi 1m, and every quotient of pi 1m of order less than or equal to g, so less than or equal to n, is a quotient of g. So if the fundamental group of M were G, these properties would be true with n infinity, because certainly G is a quotient of itself, and everything that's a quotient of G is a quotient of G. So what this is saying is if you only look at the quotients of order up to n, and the fundamental group behaves like G. It might not exactly be G, but you can't see that only by looking at quotients of small order. And I'm just taking n to be arbitrarily large, so it's pretty well to say that it looks at G if you only look at like subgroups of that. And here's the answer by myself and Melanie Wood, and I should say everything that's original in this talk will be joint work with Melanie Wood. The answer are G is either a finite subgroup of SO4, that has without fixed points, or a semi-direct product Z mod n semi-direct the 8-element returning group for n. So this is any semi-direct product for any action Q8 on Z mod n is valid. And so
Sorry, you're saying if this is true?
this is if and only if.
Yes, okay.
If and only. So G is well approximated. If and only if either it actually is a finite three manifold group, or it's on this one other infinite family of groups. So the unique non-abelian group or that's not the usual group, an odd cyclic group, and so there is some overlap between these two lists, and so some elements on this second list are not new. It's basically the action of Q8 on Z mod n factors through a quotient of order 2 of Q8, then it is already acting on SO4, and otherwise it isn't. So the smallest kind of U group has order of 1. Yes.
Give an example of this like an infinite group and just and a G that just kind of illustrates this property.
So
Because I guess you have random infinite group and a random n. I mean, there's no G that sort of.
yeah. So what you can do.
To me, Matt's asking, how do you approximate the trivial group?
For example, so I don't know an easy way of writing down. So for example, to write down a group which is infinite and has no finite quotients. I mean, or there's no small finite quotients. I mean, well, I could write down a group that's infinite and has no finite quotients very easily. For example, an infinite symmetric group, but that isn't a three manifold group. So let me give you a different answer. which is if you take a okay, oh, sorry. There's a very good answer. If you want to know how to approximate the trivial group, you can just take z mod p for p an enormously large prime. This has no quotient of order less than p. And so sometimes your approximation is just another finite group. And so let me give a topological answer, which is to make an approximation to the trivial group without applying our method. You can take a knot and do Dane surgery. So you want to cut out a neighborhood of that knot, which is the solid torus, and glue the solid torus in a different way. And then if the ways of gluing the solid torus in are given by rational numbers, basically, and if you choose a rational number that is p-adically very close to the one you started with for all small primes p, then the Funnels group of that three manifold will be an example. Because it will, for all covers of the not complement finite order, the two gluings will kind of look the same from their perspective. And so if I was good with the actual calculation of Funnel groups of three manifolds, I could like write down a presentation for such a group. I mean, so Z mod P is an example of such a group. You do the unknot. But maybe for a more interesting example, I could write down. But I don't know how to do that off the top of my head. But that is a concrete example that I've given you. And well, maybe a preview is that one of our theorems will say that these approximations are sort of very easy to stumble upon. Like if you just make random three manifolds, eventually, before too long, one of them will actually be a good approximation of this type. Okay, are there more questions about the statement of this result?
Okay, I mean, maybe just what you just said is, are we supposed to think of the result as sort of a restriction on the pi1m? I was psychologically like, what is? Again, that's related to this question. Like, it's hard for me to see exactly what kind of groups approximate things. I mean, I know you didn't give examples of that, I kind of got that intuition for, but
so
like, is it that there are lots of pi1m's or there are not so many pi1m's? I don't know. Is this result showing us there are lots of sort of different possibilities for pi1m, or is it showing there aren't any possibilities?
So, well, there's two parts of the result, right? One is restricting pi1m's, and the other is the existential, their construction of pi1m's. And the two possibilities are proven by very different methods in our work, and then the restriction ones are a little convenient when you're proving the existential result, so we're using those when we prove the existential result. And the existential result is more novel. The methods are more novel, I would say. So you could say that's the kind of the more interesting part, is to say there exist these kind of very weird pi-m's that approximate this group order 120, and I'll give a more general result soon. And then the positive statement is more novel, but then I mean, okay, the real thing I think is the fact that you have an if and only if criterion makes both sides more interesting. The fact that you can construct these things makes it interesting that you've ruled everything except for those things out, and vice versa. Okay. So let me now try to say what is the more general result this is a special case of. So the thing we are studying is like the set of all fundamental groups of three manifolds, pi1 of m for m of three manifolds. Except that we're only going to try to understand these three manifold groups via their finite quotients. We want to understand only information that we can described by looking at finite coverings of these three. And so a way to encapsulate that is to take the profinite completion. Which is the inverse limit of all finite quotients of the three manifold group. And yeah, so because we're still very early in the talk, let me say if you are not comfortable with profinite completions, you can just think that I'm talking about the groups, but I'm only going to be remembering information that you can detect by examining their finite quotients. And so this lies inside some set of well, certainly of isomorphism classes of small profinite groups. So what does small mean? It just means finitely many open index n subgroups. So these three manifold groups, they're all finitely generated, and that makes the profinite groups small in a certain sense. And so very broadly, we're trying to understand how this set sits inside this set of isomorphism classes. Like, you know, which ones appear, except this is a huge uncountable set, and this is a countable subset within it. We don't expect to have like a nice characterization. So to make our problem simpler, we introduce a topology. This has a topology. And the way that we'll define the topology is it's generated by two kinds of sets. It's going to be the set of all profinite groups where G is a quotient of X. And also the complement, the set where X and G is not a quotient of X. And this is for G finite. So this is another way of encapsulating the idea. I'm going to be concerned with the information you can determine from looking at the finite quotients only. We'll define a topology which is generated by sets where the sets are just carrying information on the finite quotients. Either some finite group is a quotient or some finite group is not a quotient. And so we have this countable set, which is now inside an uncountable topological space. And then now the natural thing to do is to take the closure. And so the theorem is we calculate this closure. And so what do I mean by calculate? I mean we give a criterion, like so this is kind of a constructive definition of the set. I say it's everything you can make from three manifolds, and we give a restrictive definition by saying what axiom does the group have to satisfy to lie in the closure of this set. So there are particular group theoretic facts that all three manifold groups have to satisfy, and every group that satisfies those conditions can be approximated in this sense arbitrarily well by three manifold groups. Yes.
So this comes from a question here, but I think it relates to what you're saying. So I have a question about this definition that, like, do you have any sorts of theorems or answers about, like, if I don't say for all n, but I say you have, like, you're well approximable up to n equals 100,000. Can you say anything about those types of groups? They're not arbitrarily well approximable, but they're like well approximable up to a certain point. Can you say anything about those?
Yes. So if you have a group which is not well approximable, our theorem will tell you it'll spit out for you a very precise statement of the form: if G is a quotient of pi1 of m, then there's a specific list of groups larger than G that also have to be a quotient. And so that will tell you it can't be n well approximable unless one of those groups, unless one of the groups has order greater than n.
Okay, great.
And then going the other way is a little tricky of saying that if one of those groups has order greater than n, then you're definitely fine, because it's harder to tell, you know, if you have a group that must be a quotient, and then a bigger group that must be a quotient, and then a bigger group that must be a quotient, and you keep going along the way, and then maybe some smaller group ends up having to be a quotient after.
Okay.
But yes, I think we can give a practical answer to that question. It just is not necessarily optimal.
And I guess like the reason I asked the question is like I feel like that's sort of an analog of like understanding like if I understand this countable set as Q, like a, sort of a Dirichlet type theorem about like how well or like Dirichlet approximation, how well approximable things are as like birationals. Is there a good analogy there? Like how fast do things approach from that countable set?
Yeah, well, if I give you for Dirichlet's theorem, I mean, asking any like your theorem, the interesting statements all of the form like for any irrational number, here's how well it can be approximated rationals, and that I don't think in the group theoretic setting there will exist a statement that is of that
Okay.
form. Like, okay, so the smallest group that does not lie on this list is S3, where we move the 3 to the bottom instead of the top. And S3, the specific result is that if S3 is a quotient of pi 1 of m, then S4 or S3 times S2 or Z mod 3 semi-direct Z mod 4 must be a quotient. And so this is order 12, 12, and 24. So like S3 is not like 24 approximable in our sense, and that produces an upper bound on like any kind of uniform result about what well approximability. Yeah, so something that's funny is these questions. I don't think anybody has really formulated the questions in exactly this way before. Of like people have thought a lot about fundamental groups of 3 manifolds, but I don't think anybody has asked the same question we do. It's like this result is like not very hard to prove, but like is it known? Like I don't think it's anywhere in the literature, you know. But this, so yeah, so like, as I was mentioning earlier, there is we already done a characterization, and there's kind of 2 parts of it. One is showing that the set actually lies within the set we say it does, and the other is that it contains the set we say it does. And the two things need proofs of very different methods. The upper bound for this set, the methods are like very much classical topology methods, and the lower bounds are more unusual. So are there more questions about this statement? So this statement is a consequence of a stronger result where we calculate the distribution of the fundamental group of a random three manifold on the same space, the set of, so I'll drop the phrase isomorphism class, and I'll just say the set of small profinite. Okay, wow, let me do it like this, up to isomorphism. So this is not completely precise because I have to tell you what is a random three manifold. And there are multiple possible constructions of random three manifolds. The one we like is a construction that was written down by Dunfield and Thurston. So, what is a random three manifold? After Dunfield and Thurston. So the basic strategy for making a random three manifold is to take a procedure that can construct an arbitrary three manifold and then randomize that construction. So the construction that Dunfield and Thurston said to use is the construction of Hegel splittings. And so the idea of the Hegel splitting is we start with a handle body HG. So it may look like I've drawn a Riemann surface, but this is really, well, you can't tell, but this is really solid and not just a two-dimensional surface. So the handle body is the interior of a genus G surface if you embed it the usual way into R3 and not some wacky knotted way. And we're going to make our three manifold by gluing together two copies of HG. So our manifold M will be HG union HG. And we want M to be a manifold without boundary, so we need to glue the boundary of HG to the boundary of the other copy of HG. Where the union is taken with respect to some sigma from the boundary, which is the boundary now is a surface of genus G. We need an isomorphism. Can I get a nice smooth manifold? We need a homeomorphism. Smooth manifold, we get a diffeomorphism. Continuous manifold, we need a homeomorphism between these surfaces of genus G. And so this is called a Hegel splitting whenever you do it. And the theorem is every manifold has one of these if the genus is sufficiently large, depending on the manifold. So when we make a construction of random three manifolds based on this idea, we will not have, thrown out any kinds of three manifolds foolishly at the beginning. So to randomize this, to understand the maps from sigma G to sigma G.
And this, by the way, that was known in like the 20s, but it's a good exercise to think about during the talk if you get bored with
how
it.
to prove it.
To prove this.
Yeah, using modern knowledge.
And how do you choose G? What's the random integer?
Oh, so we're going to take a large integer and make a limit as G goes to infinity. But let me explain. Yeah, so I'll explain the choice of sigma first.
Is there an upper bound on G?
There's no upper bound that works for arbitrary manifold.
No, if I fix the manifold.
I mean,
You can pick those.
yeah. So if one G works,
And
all larger G works. So there exists a minimum G that works, which is an invariant of the manifold called the Hegel genus. And then I'm sure there's theorems relating that invariant to other invariants, but that's not relevant to this topic. So the crucial thing is that the three manifolds we get it depends on this map sigma, but if we shift sigma a bit, then the three manifold will not change. So we only need this up to isotopy. And so the reason that I took it to be this two copies of the same handle body, so the boundary of two copies of the same surface, is because I want to think about this as a map from the surface to itself up to isotopy, which is called a mapping class. So sigma lies in the mapping class group of sigma G, which is the maps homeomorphisms. Sigma G, sigma G. And so this up to isotopy. And this group is a finely generated group. And there is a standard method to take a random element of a finely generated group, which is to take a random word in the generating set. So pick a generating set and choose elements from it independently, uniformly, at random, and multiply them all together. So this is what we're going to do. We're going to fix the generating set. And then we'll let sigma GL is equal to a random length L word in the generating set. And then for technical reasons, I want to throw the identity into the generating set. So I'll always treat the identity as one of the generators. And then we're going to define MGL to be made by taking one handle body and the other handle body and gluing it along the map sigma GL of the boundaries. So it's a random variable which depends on two parameters, G and L. And so this raises the question of how do we fix G and L? And the answer is no matter what you do with G and L, you can't prove anything, well, hardly anything, unless you let them go to infinity in some limit. So basically what we do is we study informally the statistics of MGL in the limit G goes to infinity, limit as L goes to infinity limit. And so taking the order of the limits like this is convenient. In particular, ensures that the statistics we're looking at will not depend on the choice of our generating set.
What is
It doesn't matter. So Dane twists, yes.
generating set of the map?
Exactly, of the mapping class group. Yes. So for our result, it does not matter which generating set you choose. So a traditional choice is the set of Dane twists, and so that's a good choice for us. So more formally, what I mean is we want to study the limit as G goes to infinity. Well, so our theorem has the form. We give a formula for the limit as G goes to infinity, the limit as L goes to infinity of the measure, the probability measure, the measure of distribution of pi1 of this random variable, MGL, pi1. So this is a random variable valued in this set. And so its probability distribution is a measure on the set. And I have a sequence of measures. I can take the limit. The limit may not exist, but we check that it does. And then I have another sequence that I take the limit, and that's what we calculate. We give a formula for it. And what I mean by give a formula is there exists some basis for the topology on this space, and we tell you the measure of every open set in the basis, and that determines the measure set. And so the formula, the general case of the formula is kind of long and complicated, so I'll give an interesting special case.
So this measure really is non-zero kind of along the whole. So
Exactly. So
but
yeah,
that's
so
not totally obvious.
it is not totally obvious. So the measure is clearly, its support is clearly contained in the closure. And it's a byproduct of our theorem that the support of the measure is equal to the closure. So which is saying that from our perspective, there is no three-manifold group that is very exceptional. There's no group that will appear, but that you have a 0 probability of being very close to that group, of approximating it very well. So any group that can appear, it shows up by accident. It shows up with, or you get close to it with positive probability. And so because of that phenomenon, by calculating the support of the probability measure, we have found this support. So let me give an example of our probabilistic formula. For which I need a little more notation. So I'll call it S. So S the finite set of primes. And I'll say an S group is a group whose order is divisible. It's a finite group whose order is divisible only by precedence. So if S consists of 1 prime, this is the usual notion of a P group, and otherwise it's a little more general, and in particular, if S contains 2, you might have non-solvable groups. And so the theorem, the limit as G goes to infinity of the limit as L goes to infinity of the probability that pi1 MGL has no non-trivial S group quotient. Is equal to the product over P and S. The product of J is equal to 1 to infinity, 1 over 1 plus P to the minus J. Fine with the product over G, a finite, simple, non-abelian. Right again, we have more space. Product of P, S, product of J. Product of S, G is a non-abelian simple S group, e to the minus the Schur multiplier of G divided by the order of the adult forms. So the probability is given explicitly as a product of terms. This is a finite product for the non-trivial theorem that there's finitely many non-abelian simple S groups, which depends on the classification of finite simple groups. And because of that, our theorem depends on the classification, or this part of our theorem, only this statement, depends on the classification of finite simple groups. So it's a finite product, and some of the terms in the product are these exponentials of rational numbers, and the other ones are these funny infinite products of 1 over 1 plus P to the minus J, which are an example of what's called a Q exponential. So some kind of Q deformation of the exponential. And so these two terms are kind of analogous to each other in a broad sense. Each of the terms in the product can be interpreted as an individual probability. So this one is the product probability that FP is not a quotient, and this one is the probability G is not a quotient. That probability was found previously by Dunfield and Thurston. And so this statement is saying, among other things, that those probabilities all behave independently of each other. We get the probability that none of these is a quotient, which is the same as having no S group quotients, by just multiplying together those probabilities.
Wait, what's that, H2 of G?
That is the second group homology of the group G which is also called the Schur multiplier, and it can be expressed concretely as the largest central extension, the increase in the order of G when you take the largest perfect central extension. Does anybody have more questions about this statement? So let me not give my other probabilistic example. I'll give it if I run out of time, or sorry, if I don't run out of time. I will instead go to talking about how is this result true, because that is, well, that result implies all the other results, or gives the general probabilistic statement implies the other results. So the Dunfield and Thurston, they consider this random model. They didn't just define it, they proved some theorems about it. And the main theorem they proved is a formula not for any probability like this, but for an expectation. And it's a general phenomenon in a lot of different areas that expectations of nice functions are often easier to compute than probability. So what they proved is that, let's say for Q now, a finite simple group, or sorry, not finite, sorry, any finite group. Instead of asking, is Q a quotient of the final group or not, ask how many times is Q the quotient. So the theorem of Dunfield and Thurston is that the or it is the limit as G goes to infinity of the limit as L goes to infinity of the expectation of the number of surjections from pi1 of M Q that mostly there is equal to the order of Q divided by the order of the first homology of Q times the order of the second homology of Q, which I can re-express without homology as the maximum over Q prime to Q as central extension of the order of Q prime divided by the order of the abelianization of Q prime. So there's some explicit, relatively nice group theoretic formula for the average number of surjections from a final group to Q. Another way of saying that is for counting the number of coverings of the three manifold with fundamental group, with covering group Q. Galois or deck transformation, or whatever you call it. And so why is this possible? How can you do this? It's because a covering is a geometric object, and you can think about a covering of M. It has to come from a covering of HG and another covering of HG that have to agree when restricted to the surface. And so you have to you get to count those things. You can count them by thinking about the set of coverings of HG inside the set of coverings of sigma G, and how does the mapping class group act on it. But it's very crucial that you have to like average over the action of the whole mapping class group. And so when you're doing that, it's totally opaque which other groups are not quotients. And so you can only calculate, at least by directly applying that method, you can only calculate this expectation and nothing else. And so the kind of problem is from these expectations, can you calculate the probabilities? So this is a problem that is really not a problem about three manifolds at all, or at least it's about three manifolds. It's entirely motivated by three manifolds, but the methods you need to solve it have nothing to do with three manifolds. It's entirely about groups on the one hand and probability distributions on the other. So it's kind of algebra and analysis rather than topology. And it's really some kind of analog of this very classical question probability theory is when is a measure determined by its moments? So I want to think of this expectation as being like a moment, as being the expectation of a natural function on our probability space, the set of small profinite groups up to isomorphism. And I want to know, do I have enough expectations of enough functions that I can calculate the distribution? And the classical answer in probability theory is you can, as long as the moments do not grow too fast. And we prove a version of that statement for measures on groups. We show when the distribution is determined by its moments. And it like almost works here. There's a slight subtlety that you need to bring in a little more information to make it work. But it works nicely with that extra information, and it works. It becomes very close to working without that information. So let me say that the nature of the extra information that we calculate and use. So the first additional piece is if you have a surjection from the fundamental group of M to Q, there is an additional piece of data that comes with that, which is the fundamental class of M lives in the third homology of M. And so you push it forward to the third homology of Q. So every surjection comes to with a class in the third homology of Q. And so rather than counting surjections, a more refined question is to calculate how many surjections have a given third homology class. And so you might naively guess they're equally distributed. And if you do that, you would see you have to put in the denominator the order of the third homology, and that looks like a very elegant formula. So then you would really start believing it's true, and then we check that. We check that that is true. They are evenly distributed for G large using just like a slight elaboration on the method of Dunfield and Thurston. And then the other piece of information you need is some of the positive facts, or the restrictions we proved on fundamental groups give you restriction of support in the measure, and they turn out to be helpful in reconstructing the measure from moments. In particular, there are facts about parity, about when the cohomology of a certain representation of this group has even or odd dimension, and those parity facts are kind of crucial to deal with the moment issue. The other thing I want to talk about, and really I think the most interesting thing, I'm very sorry to the people that had to leave. Well, I guess okay, I Yes, I'm sorry, but maybe I shouldn't say it in exactly that way. But maybe they'll enjoy if they catch the videos after watching this apart. Is these methods that for determining the measure from a moment are applicable in a wide variety of situations. So in particular, we give general criteria for the existence and uniqueness of a measure U on on the set of small profinite groups. With the expectation of the number of against the measure mu of the number of surjections from x to g equal to some fixed function of g. So if you give me for each finite group a number which is supposed to be the number of surjections, and tell me, and then I can tell you, at least if the numbers don't grow too fast, I can tell you whether there exists such a measure with those moments and whether it's unique. Yes.
It looks like this result gives us the.
So, well, it's not a distribution on numbers, right? It's a distribution on groups. So the classical notion of moments on group is not defined for regular groups. So I get to define it. I'm just defining this to be the moment. That is kind of a bad answer. Let me give you a better answer. So the first better answer is that this number, if I raise it to the nth power, I get it counts n tuples of surjections. So the moment of this is a number, the number of surjections is a random variable. The moment of that random variable count n tuples of surjections. But an n tuple of surjections gives me a surjection to a subgroup of the product group. And if I sum this in a suitable way over subgroups of the product group, I recover the nth moment of the original value. So the sum over certain subgroups of q to the n of this kind of surjections gives me the nth power of the number of surjections for q. So I do have the moments of all functions of this form. The problem is, unless q is like a finite simple group, just applying the classical theorems about when a measure on numbers is reconstructed from its moments will not recover the distribution, even just of this number, let alone of the full group. It works for finite simple groups, great. It doesn't work for other groups. And so by passing to the category of groups and doing the reasoning there, rather than the reasoning in numbers, you gain the advantage, which lets you actually calculate the distribution. Okay, and the second explanation is surjections from pi1 of m to g are roughly the same thing as Hom from pi1 of m to g. And you can get from one, and they're not the same, but you can get from one to the other. So we carry the same information. And then this is the same thing as the Hom in the opposite category from pi1 of m to g. Or some g to pi1 of m. And you write that, you are allowed to write that sometimes pi1 of m raised to the power g. So if you think about a moment as a power categorically counts homomorphisms, then my moments are powers just in the opposite category. So somehow we should have been working in the opposite of the category. But I will work in this category because in every example I know of, but no, it's not true every. Most examples I know of, not in every one, this category is more natural to consider. The opposite of the category is a weird category that people rarely consider. So we give a criteria. Well, actually, we give a criteria for existence and uniqueness, and we also give a formula. So when it's unique, we don't just say it's unique. If you found it, you know there was only one. We actually write it down for you. So this criterion we expect to have applications in other areas of mathematics. So one area where people study profinite groups a lot is number theory. People study Galois groups. And there are areas where people look at random Galois groups. And this was in fact our original motivation to study random Galois groups. And then we decided to try applying the method to three manifolds as well. The result is more general than that because it doesn't just apply to groups. It also applies. We tried to write it as generally as we could, and it also applies in other categories to things like profinite rings and profinite modules. And some other algebraic structures. So profinite groups are very commonly discussed. I haven't heard people talk about profinite rings and profinite modules as much, but a profinite ring, and a good example of profinite ring is any complete Noetherian local ring with finite residue field. And there are a lot of those in mathematics. So there are a lot of cases where the profinite ring shows up. And then any complete module over such a ring is a profinite module. So a lot of different algebraic structures that appear in mathematics, we have a tool for finding probability distributions of them, for defining them, to showing they're uniquely determined by their moments, proving existence, like calculating them. A tool for a lot of things that you might want to do with these distributions.
But for your results, do you like quote the Dunfield Thurston to get the moment? And then
No, we
quote it
don't.
many times to get all the moments, and then
Well, you only have to quote it once to get all the moments because that's how
there's
quoting.
powers that, I mean,
Well, no, so the power thing is not how we think about it in the paper. We don't consider such powers in the paper because it makes sense to work on the level of groups and not on the level of numbers. So we don't end up quite quoting Dunfield Thurston because we want a slightly stronger result. So we have to redo their proof. If we did not want that slightly stronger result, we would have just quoted Dunfield and Thurston. But it's so close to the original proof, you could consider it a quote.
but then, so we consider that part is where you're really using like the specific random model and free manifolds. And then part two is is like a theorem of probability distributions on
Yes,
groups, on
exactly.
spaces of groups, whatever.
Yeah, so in our first paper, we didn't extract the general theorem about groups because it was more convenient. So if you wrote the theorem only with this specific list of moments and no other, it would not be useful probably for any distribution, except maybe some other models of random three manifolds have the same moments.
Right.
That's why we didn't write it in general. But then in our second paper, we tried to do it in general for any distribution or in any set of moments of random groups that don't grow too fast, and also for kind of other categories.
But the input to that kind of machinery, you have to have the quote unquote first moment, yeah.
Yeah,
And that's
you need the moment.
specific
Yes, and so
problem you have to act, that's probably,
yeah, so this is motivated by settings in number theory where the moments are either easier to calculate or at least they're easier to guess. You sometimes the distribution is so hard we can't even guess what it is, but the moments we can guess, and that gives you a conjecture for the distribution. And we hope it will be applicable to more settings, for example, other models of the three manifold. However, you need to get the moment first. Our ideas don't really help with that much. Yes?
So a question about like how much power you can get out of it. So one of the ways you might want to measure like complicatedness of a Herodite splitting is looking at the entropy of the mapping class, right?
Yes.
And you could say like, okay, if I surject onto a finite group that I know, then maybe I expect my entropy to be higher because I have to do more stuff in order to surject onto that group. Can you calculate that, like the expectation of sigma GL conditioned on like surjecting?
The expectation. Okay, that is it. That is a great question. I mean, it's a very simple answer, which is no. We cannot calculate anything about any other invariant of the mapping class of the three manifold that doesn't come directly from the profinite completion. I will say that the trivial mapping class gives you a very big ocean, gives you the fundamental group of the handlebar. And so it's kind of the reverse of what you said. I think the mapping class has to be highly non-trivial to make the quotient small, and the trivial ones will give you a large quotient. Okay, but maybe I should, okay, especially because people are, maybe I should stop here, and then this is like the official question period. Thank you for inviting me to speak.
Other questions?
I guess this is a very vague question. So you were saying that there's something inserted to like as moments from the number 30 side. So what is an example?
So well, let me be a little imprecise. So the profinite group with the number theory setting is a Galois group, and so finite quotients of it correspond to number fields. So moments are related to counting averages of the number of number fields. So one example where you can compute these averages is like the number of number fields with Galois group S3, S4, and S5 of bounded discriminant is computed in S3 by Davenport and Heilbronn, and S4 and S5 by Gava. So those are some examples where you can compute the average number of like number fields, which gives you some kind of moment of something. But what you can do better is in the function field case, computing average numbers of function fields in some kind of large Q limit. We know how to do that using kind of geometry and actually topology as well. And so then you can just guess that the average is the same in the number field case. And so those are some cases where you can get. I can say more in detail if you catch me later. Yes.
Is it a coincidence that this Dunfield-Thurston formula, like this product with Q, H1, and H2 looks like product for the zeta function of the finite, the curve over a finite field?
That is a good question. So I don't know. I mean, it looks like a lot of things. I mean, so this kind of product, I mean, you could also say it looks like the exponential of an Euler characteristic, because the Euler characteristic is like dimension of H0 minus dimension of H1 plus dimension of H2. The weird thing is I am truncating it. I'm stopping at H2, and if I put the extra data, I would stop at H3. And the fact that it behaves like a truncated Euler characteristic is very convenient for us in calculating the probabilities. To somehow, Euler characteristics have really, really good invariance properties. They're very well behaved, and these truncated Euler characteristics, they're not quite as well behaved, but they're still very well behaved, and it's well behaved enough that it helps us in doing the kind of very complicated linear combinations of these you need to get to spit out the probabilities. So in that sense, it's kind of not a coincidence that like it's helpful for the it's helpful for getting this kind of like nice product formula. We would not be able to get this type of product formula if you just put some arbitrary formula in H1s and H2s and H3s in here. But it's hard to say that it's not a coincidence because I don't have enough other examples. So okay, I wrote down the previous formula, which is QH1, QH1Q, and then and then those should come with a class in H2, and then you divide by H2 if you keep track of H2. And I made a random model for that. It's not so hard, and I can show uniqueness. I'm pretty sure, but it's a weird random model. It's like you take a genus G surface and you just add 2G random disks to it. So it's not any kind of manifold. And then I tried to go up by one, and then the moment result is very, very far from working. So I have no idea if there exists any distribution with those moments, if there's lots, if there's one. I have no clue. So, and I don't know if it comes from four manifolds either. So it seems like something is going on, but I don't have a good explanation of exactly what it is.
Anyway, with that, let's thank Will.